Alright, so it's a little evening activity here in the Jarvis household. As you can see, we're downstairs in the Jarvis basement once again for another exciting geometry lesson. We've got little man over there interested in watching the fire and actually wants to learn a little something about proofs tonight. So let's have a seat and we're going to go ahead and get started. Alright, if you have any questions, bud, just speak up. Anyway, we're looking right now, we just sort of finished that introduction to proofs, which dealt with algebraic properties and algebra problems that you were used to looking at in Algebra 1, and being able to go through a proof of how to solve for a particular variable using the properties from algebra. So it was real easy, or hopefully it was a step in the right direction in getting you to understand how to justify your lines with a two-column proof. And then we actually made the segue into looking at segment relationships and angle relationships. So I just want to go through one on the board. Alright, so let's take a look at the segment addition problem I put on the board here. And we're basically looking at given the length of segment AB is equal to the length of segment DE, meaning they're congruent. So the one thing you want to get in the habit of doing is marking off what's given in the diagram. The length of segment BC and the length of segment EF have the same length, so we're going to mark those off congruent as well. And we're trying to prove the length of the whole segments are equal to one another. So as we set up this proof, again, we said 99% of the time, what are we going to start off with? The given. So I'm going to put AB equals DE, and we're going to put BC equals EF. Well, if we're trying to prove that those whole segments are congruent or equal to each other in length, what do you think I need to do with these two pieces? Well, as we look at it, again, if I said this was 2, that would mean this has a length of 2. If I said segment BC had a length of 4, that would mean segment EF has a length of 4. If this was 2 and 4, the whole thing would be exactly 6. Same thing on this segment. If I look, that was 2 and that was 4, the whole thing would have a length of 6. Again, showing that they both had a length of 6, meaning they're both congruent. So what did we just do with the 2 and 4? We added them together. So what do I want to do with these equations? I want to use the addition property of equality, which would let me add two equations together. Add what's on the left together, add what's on the right together. So that's going to give me AB plus BC equals DE plus EF. Just sneak that in there. Now, we at least have these two pieces added together. I want to get segment AC somehow involved in an equation. Well, if you think back, we had all the properties from algebra that we could use, the postulates and theorems that we've done so far in geometry, and the main one being, I think the first big postulate we looked at was the segment addition postulate. Let us add two pieces together to get the whole piece. So again, I could say segment AC is equal to AB plus BC. I can use the same reason for the other statement. Segment DE plus segment EF equals the length of the whole thing. So I can say segment DF is equal to DE plus EF. Again, that was the segment addition postulate. We said we could abbreviate it SAP, but until we get comfortable with it, I'm just writing it out that way. And lastly, now what can I do? If AC equals AB plus BC, then using the substitution property, wherever I see AB plus BC, I can substitute AC in its place. So we're really taking this, substituting it there, and we're going to take segment DF and substitute it in on the other side. That's going to leave me with the length of segment AC equals the length of segment DF, and we just used substitution. Alright, here's just a little twist on what we just did with segment addition. Because now I've got just one segment. It's broken up into a couple pieces. But we're given that the length of segment AB equals the length of segment CD. We're trying to prove that segment AC is equal to segment BD. So let's see if we can set this one up. Again, two-column proof. We've got statements and reasons. 99% of the time, what we say we start off with? The given. I know, hard to believe, right, Jeremiah? So we got AB equal to CD. Now again, you're trying to develop this thought process of how we set up a proof and where we go with it. if I look at what we're trying to prove, segment AC, what's that made up of? AB plus BC. If I look at segment BD, what's that made up of? Segment BC plus segment CD. So what do I have to add to AB to get segment AC? We just said segment BC. Likewise, what do I have to add to the other side? So again, if I'm going to add BC to both sides of an equation, I've got to get that up on the board somehow. It's not like we can simply use the algebraic property of just adding the same thing to both sides, because we're dealing with lengths of segments now. But this is where that one property that we talked about is going to come into play. Everybody remembers the reflexive property? And the reflexive property lets me say that a segment is equal to itself. So it lets me say segment BC is equal to segment BC, congruent to itself. What can I do with these two equations? Add them together. That's going to leave me with segment AB plus segment BC is equal to segment BC plus segment CD. Again, the lengths of those segments. What did we just do with these two equations? We used the addition property of equality. So I know that segment AC is made up of those two pieces. I've got those two pieces on the board. I still need to get an equation that involves segment AC and to get an equation that involves segment BD. What comes into play? Our good old friend, segment addition postulate. Remember, the segment addition postulate lets me look at a segment, and if I've got a segment that's broken into a couple pieces, I can add those few pieces together to get the whole segment. Little man over here is having trouble with this one. So we're going to say AB plus BC equals AC. Again, that's the length of segment AB plus the length of segment BC equals the length of the whole segment, AC. Same argument, or same reason I should say, as BC plus CD equals BD. What can I do with these two now? Wherever I see AB plus BC, I can substitute AC in its place. Wherever I see BC plus CD, I can substitute BD in its place. That's going to leave me with the length of segment AC equals the length of segment BD. Hard to believe, huh, Bev? I think he's almost ready for bed. But we just used the substitution property, and we're done. I want to set up a similar problem with angles. See if you can do that one on your own. Alright, let me give you a second to copy that down. Almost identical proof as the one we just did, except instead of dealing with segments, we're dealing with angles. But we're given angle 1's equal to angle 3. Notice they both involve angle 2 somehow. We're trying to prove angle AEC is congruent or equal to angle BED. And again, if you use the last proof as sort of a blueprint, that should set you up on how to set this one up. This is one of the problems I want you to have done for Thursday. I'm going to set up another one with segments, and then we're actually going to talk about our first theorem after this. Alright, so here's a proof involving back to segments. Again, we're dealing with sort of the tricky situation. Calm down, little man. Tricky situation with segments. And you're given Jn equals UE. You're trying to prove Ju, the length of segment Ju, is equal to the length of segment Ne. And again, look at that first proof. Instead of going from smaller pieces to the bigger pieces, we're sort of doing the reverse. So think about what you have to do to set that up and see if you can come up with that proof for Thursday. Now, the last thing I want to take a look at is a theorem, and it deals with complementary angles. And we can apply the same thing to supplementary angles, but this one talks about complementary angles, and it talks about angles that are complementary to the same angle are congruent. So let's look at how we could set this up. Let's make it to the same angle. So I'm going to say angle 1 complementary to angle 2. This is in the given. Angle 3 complementary to angle 2. And we're going to try and prove angle 1 is equal to angle 3. We don't even need a diagram for this one. And set it up with statements and reasons. Hard to believe, right, bud? So we're going to start off with, the, you guessed it, given. Angle 1, complementary. Angle 2, angle 3, complementary. Angle 2. Now, you might ask, if they just tell us two angles are complementary, remember, things we can use as the reasons. Given information, properties from algebra, postulates, we've used those already, some theorems, this is actually a theorem we're trying to prove, definitions. Have we defined complementary angles? And we have. So if we've defined it, chances are we're going to use it whenever we see it. So definition, complementary angles. What does it mean when two angles are complementary? Again, two angles are complementary if their sum is 90, if the two angles add up to 90 degrees. So if they're complementary, I get this equation. Angle 1 plus angle 2 equals 90. Angle 3 plus angle 2 equals 90. If this stuff equals 90 and this stuff equals 90, what's true about the stuff? Again, by substitution, I can take angle 3 plus angle 2, and wherever I see 90 in another equation, I can substitute it in its place. Angle 1 plus angle 2 equals angle 3 plus angle 2. Substitution. We're close to what we're trying to prove. We got an equation that involved angle 1 and 3. Second, we got an equation that had angle 1 and 3 in the same equation, but we have some other stuff we need to get rid of. How do we get rid of the angle 2's? Subtraction, right? If we wanted to be technically correct, we'd have to throw in here the reflexive property to say angle 2 equals itself. And don't forget, the subtraction property of equality lets me subtract two equations if they're equal. These are equal. This equation, they're equal. I can subtract the two. What happens to my angle 2's? They cancel out. We're left with angle 1 equals angle 3. We just use the subtraction property of equality. Go ahead and copy that down. And actually, this is a theorem. We're going to write. You can pause it and copy it down. I know I started erasing it, but I'm trying to save some time here. But we can write this theorem rather short, and it goes like this. Complements of congruent angles congruent. Complements of congruent or the same angle, because if it's the same angle, it's congruent to itself, are congruent. Now there's a similar theorem which deals with supplementary angles. I'm going to set that one up and see if you can solve this, or actually prove it on your own. So we would start off given angle 1 supplementary to, let's do it this way, angle 3, we're going to say angle 2 supplementary to angle 4. This time we're not going to make them supplements to the same angle, but we'll make them supplements to congruent angles. So also in the given, we're going to have angle 3 is equal to angle 4. Prove angle 1 equals angle 2. Go ahead and set that one up and see if you can solve that. And when we get back on Thursday, we'll go over this stuff and just keep plugging away on this chapter as we get used to dealing with proofs, setting up the flow of the proof so it makes some sense and goes through it in a nice way. So I hope you guys had a good Tuesday and Wednesday without me, and we will get going again on Thursday. And I think it's someone's bedtime. See ya. Look at this guy here. It is definitely past his bedtime on a Monday night. Yet, we're doing proofs and the boy's wide awake. He's like, show me those proofs, Daddy. I can't wait to get to them. So someday he's going to be doing these just like you guys are doing.